Welcome to today's Research Pays Off. I'm going to hand it over to our speaker, Dan Swiertz of Asphalt Materials, to provide a summary of the recently completed project, Materials-Based Methods to Improve Rumble Strip Durability.
All right. Thank you, Lauren. Thank you for spending an hour with us here today, everybody. Again, Lauren mentioned my name is Dan Swiertz. I'm here representing Asphalt Materials, Inc. We're going to really just focus on the actionable, more implementable items that came out of this recent study. The title shown here on this page, the Materials Methods to Improve Rumble Strip Durability. As Lauren mentioned, if there are questions, I suspect there will be. There'll be plenty of time at the end. Put them in the chat, and she'll facilitate a Q&A session for us. Some quick housekeeping. The way that this study was set up, when we use the term rumble strip, what we mean is milled centerline rumble strips milled into new asphalt pavement, so at the time of construction. Some of the findings undoubtedly can be applied to rumble strips milled at other time frames in an asphalt pavement, perhaps even different types of structures and shoulder rumble strips and so forth. But for the purposes of what we're presenting, these are milled centerline rumble strips into new asphalt pavements. To follow, here we go. Some of the project details, and you can peruse this at your leisure by following this QR code to the NRRA website. This is a co-sponsored project from the NRRA. We completed it just recently, actually, within the last month, but these projects were built in 2023. The major outcomes, there's a final report that will have the full breadth of data that we won't get into today, but there'll also be a standalone functionality report. We'll talk about what I mean by functionality. And then there's like an infographic. It's just a one-page printout that you can use that's just sort of a practical outcomes of the study. You can think of it almost like an even shorter tech brief if you want. Acknowledge the other researchers that joined us on the study, Heritage Research Group from Indianapolis and Banky Materials Engineering, providing a lot of the field support here in Wisconsin. So the genesis of this project is fairly straightforward. Many states, and my state's Wisconsin, but many states are seeing centerline rumble strips being used on a higher and higher percentage of design scenarios. And the reason for that is that the data is overwhelming, that centerline rumble strips really are among the most cost-effective safety countermeasures that pavement designers and engineers have at their disposal to reduce lane departure crashes. There's no doubt about it, they save lives. But from the lens of a materials engineer or pavement engineer, we know that centerline rumble strips, when built in sort of a, let's call it like two-lane highways, are milled into or at least near a vulnerable area of the pavement. So at the joint, at the location of the centerline joint, there's both a physical, but also a mechanical discontinuity, right? Mechanical property discontinuity. And as you move, let's say, from the main line to the joint, properties like density, say, for example, density will change as you get closer to the joint. What that trend looks like is likely dependent on construction practice, mixed design, and so forth, but we know that mainline properties typically are not representative of the joint properties. That's in a transverse direction, but we also will show a few slides later here how some of these properties, again, take density as an example, also change from the top of the mat down to the bottom of the mat, right? So there's also a vertical element of this. So rumble strips milled into a vulnerable area of the pavement. So the research question that naturally follows then is, do rumble strips damage the pavement at the longitudinal joint? Another way to ask that is, do they create the conditions that facilitate accelerated damage? So a couple of days back, I heard a colleague use a term that I really like, and I'll use it a few times here throughout the presentation. Another way to ask this is, our centerline rumble strips damage multipliers? In other words, do they create, in a vulnerable area of this pavement, do they create the situation where any distresses will be multiplied with time, traffic, and environmental conditions? So that's the sort of the genesis of the project. And now We're absolutely not the first research team to ponder this, but nevertheless, still comparatively little has been done, and certainly little has been published with regard to the effects of rumble strips on pavement durability. Certainly the safety side of things has seen quite a bit of work done. And I think the reason for this is potentially twofold. One is very obvious. It's extremely difficult to simulate milled centerline rumble strips in the laboratory on a longitudinal joint, right? Most of our laboratory testing surrounding pavement materials is testing the component parts. So maybe that's asphalt binder, maybe that's aggregate used in the mix, or it's testing the mixture compacted in the gyratory kind of as one homogeneous sample, right? So all of these new performance tests like ideal CT, and so forth are meant to test the composite material. But we don't really simulate joint construction in the laboratory, and we certainly don't simulate rumble strip milling in the laboratory. So simulation is one. Another is that a lot of times, at least in my experience from the literature, is you don't see a lot of cross-management type of research studies, and I'm talking about like management silos in terms of materials folks, construction folks, safety folks, and maintenance folks all kind of coming together and saying, here's a research study that deals with all of these things. So that could be another reason why you don't see it. Still, why you don't see it in the literature as often. Still, there have been some survey style and also some primary research that's been done looking at the effects of rumble strips. I list a few of them here. Of course, the literature review for the project is much more extensive than this. But the bottom line from the performance aspect of the literature is that this seems to be a topic that's not settled. There's some evidence that rumble strips may change sort of the physical nature of the joint. That's a study here, DiCarlo et al., showing differences in water permeability. Now, water permeability is not performance, but it could be a surrogate for performance, especially in heavy freeze-thaw regions and so forth. Another study, this one from out in Oregon, this is this gentleman's published work based on his thesis, used CT imaging to show microcracking near the surface, at and near the surface when rumble strips are built in. Again, microcracking is not performance, but perhaps it has something to do with long-term durability and so forth. So again, sort of unsettled effects, but some indication that the rumble strips are at least changing something. Are they damaging it? Remains to be seen. What a good literature review should do is it should shape the design of your experiment, right? And as we were developing the research hypothesis, design of experiment for this study, there's an ongoing NCHRP project, and the number for that NCHRP is 1568. It's since been published as report 1107, but that NCHRP study focused strictly on functionality. How do the rumble strips work as life-saving tools, as driver alerting tools? And what they found was that geometry, it probably naturally follows, geometry strongly impacts the functionality. How deep you mill these rumble strips, the wavelength, in other words, sort of like how large the impression that you mill into the pavement affects the functionality, the noise. And interestingly enough, this also includes geometry after treatment, right? And that should be logical. In other words, if we treat the rumble strips with something that changes the geometry, likely the functionality is also changed. We did a state survey among the NRRA states for the different geometries and methods that were used. And it's probably no surprise that there's little standardization among NRRA states and indeed across the U.S. in terms of rumble strip geometry. In other words, how Wisconsin builds a centerline rumble strip is not the same as how Iowa does it, despite sharing a common border in an area, right? So similar climate, similar traffic, but they do these things different. So what that meant to us is that likely setting up some research study will have to somehow look at geometry, both in terms of how the rumble strips are built, but how any treatment plan impacts geometry. So we're beginning to set up our research objectives, and they're shown here kind of in more simplistic terms. The first is a very basic question. Do they damage the pavement, or do they create conditions that facilitate accelerated damage. Do centerline rumble strips do that? If that's true, so in pursuit of that, and this follows sort of that that long used pavement preservation mantra, right treatment at the right time. Well, in this instance, the right time is time t equals 0. Either before these things are milled or immediately after they're milled. Can we use material treatments to offset any of that damage, promote durability of not only the centerline rumble strip, but of the longitudinal joint? And then as we mentioned on the last slide, we really need to understand we're investing in rumble strips as a safety tool. Are they maintaining their functionality as a safety tool after treatment? This map here, the lower half of the state of Wisconsin, a little bit of a teaser, but how we built this project, how we set up the work plan for this project, is we use full-scale construction projects, and you could say like real world. I don't, that's kind of an odd term because everything is real world somewhat, but you'd say representative of in-service conditions. Wisconsin's a relatively unique state in how counties manage their pavement networks. Suffice to say is the 3 counties that have the red stars here, Wood, Sheboygan, and Rock, maintain their own paving operations. 2 of them even maintain their own hot mix plants, but their own paving operations. So we approached these 3 counties who agreed to help us with this project. We said, during the 2023 construction season, select a project that you do nothing different than you normally would do, but we would like to install centerline rumble strips on a portion of that project, material treatments on a portion of that project, and monitor this with time. Take cores, do our serviceability testing, our functionality testing. And what we selected were 3 2-lane undivided county highways. So very representative of rural highways that you would see all over the United States. These would be paved 1 lane at a time, not in echelons. So pave one side, pave the other side, constructed using their standard practice. We said, whatever your structural design, your geometric design, don't change that. We're just going to be implementing these treatments. In each of these 3 projects, we have areas with and without rumble strips. To speak to the geometry during construction portion, geometry of the rumble strip I'm talking about, one of these projects utilized WSDOT's sinusoidal rumble strips. Those are sometimes called mumble strips in our industry. These are those continuous kind of sine wave rumble strips. The other 2 used, I call them standard WSDOT geometry, but they're the paired corrugated rumble strips, the kind of half moon shaped rumbles. And I'll have some pictures of these coming up. So now we have control versus rumble strip. And then we chose 3 treatment strategies. And I'll kind of tip my hand a little bit. One of the major developmental portions of this project was extensive cost share among industry and the NRRA. And these treatments were both the material and the process donated to the project. So we had a different toolbox to choose from, but we chose 1 pre-construction treatment. And what I mean by that is before the rumble strips are milled in this instance, before the surface layer is paved. The second, following construction, I call it post-construction. This was an asphalt fog seal applied to the milled in rumble strips. And then the third is just a combination of the 2. So hit it from before, hit it from after, and see what happens. So if we count control versus rumbles, 3 treatments each of those in each of those sections, we have 8 research cells per project. And we were successful in getting all 8 on all 3 projects. Minimum lengths of about half a mile per research cell for a few reasons. A lot of it's logistics, right? It's difficult to apply these things on smaller sections. But second is the functionality testing requires some unbroken stretch, literally just to drive across the rumble strip over that stretch. So there's some length we need for the vehicle to safely get up to speed, hit the rumble strip for a length of time, and then decelerate. These are live traffic scenarios. We had to minimize our impact. So these other projects were set up. All of them were constructed the same way. So what I mean by that is they were full reconstructions. These weren't mill and fills. These were full reconstructs. So pulverize, actually all 3 of them pulverize the existing structure, build from there. So what you'd be looking at here would be a paved Wisconsin calls them lower layers. Some folks call them base layers, the underlying asphalt pavement ready for surfacing. In each section, where applicable, for the pre-construction treatment, we use a treatment called VRAM, void reducing asphalt membrane. This is a treatment that's a hot applied polymerized asphalt. It's applied at the location where that surface joint will occur. So it's applied to the base layer, to the lower layer, underneath the surface layer, and we'll pave on top of it. So it's applied at an 18-inch, in this instance, 18-inch width band. So it's covering both the joint itself, but also some gradient away from the joint, 9 inches in this instance. Once that material cools to about 130 Fahrenheit, a few minutes only, it can be paved on, driven on, etc. So it's pre-construction because as we pave the upper layer, our first pass, you could call it the unconfined pass, covers half of the VRAM, right? Compact as usual. And then as they match for the day, so maybe they pave 2 miles, the next day they come back and match up that 2 miles. However the county chose to do it, the next pass would cover the rest and pinch in that cold side. So here's paving of the upper layer on a VRAM section. That's why it's called pre-construction. It's put down before the upper layer. In each of the 3 projects, we instructed the counties, you do quality control as you would usually do it. We'll be out here measuring quality control as we would do it. So whether that be nuclear density testing and so forth to monitor consistency along the project, but we didn't change their process. Whatever their process was, they stuck with it. This is just an example photo of a nuke density meter at a unconfined joint as an example. We also collected plant mix, and that'll become apparent why we did that throughout the project. So that was taken, you'd call it plant mixed lab compacted for the research portion, the lab portion of this study. In the designated sections where rumble strips were milled, we solicited the help of local contractors. Here you can see milling of standard WSDOT geometry, and that's shown here. WSDOT standard geometry is a maximum mill depth at the center of this rumble strip of half of an inch below grade, tapering to grade, obviously, at the edges. And these are paired. So this pair would be an 18 or 24-inch offset from the next pair, and so on and so forth down the line. Centered at the location of the joint, which in this instance you can see we missed it just by a hair, but the joint would be where my laser pointer is shown here. One of the projects got the WSDOT sinusoidal geometry milled in. Here's a picture of the sinusoidal geometry. The max mill depth on WSDOT sinusoidal is still a half of an inch, same as the corrugated paired rumble strips. The main difference here is that waveform just cracks the surface. So it is recessed very slightly below grade, even at the top of these waveforms, but it's a sine wave, hence the name, sinusoidal. Different states have different geometries. WSDOT's is a 14-inch wave-to-wave length. And those are all available, all the geometries are available in the final report for both WSDOT, but we also summarize the NRRA states. When the design section called for it, for the post-construction treatment, this is an example picture, representative picture of the centerline fog seal. So we used a penetrating asphalt emulsion to fog seal the joint. So this would be a treatment through standard distributor, somewhere around 1/10 of a gallon per square yard treatment on down the length of the pavement. From there, the pavement would be or was striped, open to traffic, and away you go. These are our live section roads. Our study focused on lab testing of field samples. So we cored each of the 8 research cells, 12 cores per research cell per project. And this is the way we laid them out. We chose to do offsetting the cores about 16 or 18 inches in one section of each of the research cells. And we did that to minimize variability along that cell. So in other words, just take advantage of the cores being kind of grouped together, assuming that was a representative area within each cell. The other reason we do that, I alluded to, is we needed as long of a call it runway as possible for our noise testing, because they need to get up to speed, hit the rumble strips, get off the rumble strips safely. And we didn't want the core holes to interfere with that. When I talk about functionality testing, the way that this is done, there's both internal noise and vibration. So this would be like the driver alerting portion of the rumble strip, but then there's also external noise. And external noise is measured simply with a microphone placed offset from the center line, a pre-designated distance. And what the folks do is, you can see this vehicle here gets up to speed, merges onto the rumble strip with the driver's side wheels and just stays on it. So it's just a long day of driving on rumble strips over and over and over again. And they record several passes, average, move to the next cell, and away we go. So this happens to be from the Sheboygan County Double L project, but this is how the noise and vibration testing is conducted. We desired to design a lab experiment around these cores that maximized research output while somehow being practical and simulative of that joint as well. So what we chose to do is all of the cores that came in, the upper layer of the pavement is sliced off of them. So remove the lower layer. Now we just have our upper layer, and physical and gravimetric properties taken. So measurements of height and all sorts of different dimensional analyses, bulk specific gravity and so forth, the non-destructive type of testing. And then from there, the cores were randomly distributed into their destructive testing elements. So we chose two primary destructive tests. The first, ideal CT, that test was chosen for practicality. It's being used not only among NRRA states, but a wider and wider range of other DOTs and local agencies. It's easy to use, it's practical. Obviously, there are questions with its ability to screen certain materials, but in our instance, we chose it. Widely used, a large body of literature available to compare results to. In other words, we have something to bounce results against. And you can see how that test setup would be shown here, tested along the length of the joint, right? That's how we would test those samples. The second test that we chose is a modified Texas overlay test. Now, a much less used test among state agencies, but we thought a very interesting tool for our case because of how it simulates movement at the joint. So the setup for the Texas overlay test, the way we set it up, is shown on the left here. And you can see where that joint would be. It's this pink line. And what happens in that test, as we'll explain, is one of these plates moves relative to the other. The sample is affixed to the plates. So it's simulative of a joint kind of moving relative to itself, relative to the other lane. We can measure a few important properties that way. And then there are others that are again, more research-based tools, water permeability testing, asphalt content and gradation kind of standard testing. So get the most bang for each one of our cores that we can, while also trying to simulate and be practical with what we're doing. Kind of starting way at the top, at the very baseline level. And the way I'm choosing to show this group the results is just kind of an example from each of these tests. Maybe it's, in this instance, it's just one county. In some instances, it's all 3 counties, but just a couple of research cells each. The final report obviously contains all of that data. And the conclusions that we draw from it are taken from all of the data in aggregate, not just what I show here. So I'm just kind of picking reasonable representative results from each of these to show you. Here we're looking at extracted aggregate gradation. So this would be solvent extraction, simple wash gradation. And what we see, and this is consistent project to project, is really these lines for all 8 of these research sections in this particular project overlaid amongst one another. In other words, really no significant degradation due to milling of the centerline rumble strips. It is important to note Wisconsin, at least at the county level, and a lot of the state work as well, tends to produce their mixes as dense graded fine. In other words, they're very fine graded. They typically would fall well above the max density line. We have very rich deposits of sands and gravels that we use. We've also just have a long history of using fine graded mixtures. Is this true for coarse graded? We can't say. SMAs, we can't say. But what we can say is for the 3 fine graded mixtures that we used, there was no significant degradation due to the milling of rumble strips. Maybe more interesting, air voids and total binder content. So if rumble strips are shown to increase permeability, which there is some research linked to that, there has to be a reason. And one of the reasons would be interconnected air voids changes. And what we found is that milling of centerline rumble strips, when taken as an aggregate across all 3 projects, in general increased, but it was insignificant and it was highly variable across sections. In other words, it didn't always increase. It was just on average, it slightly increased the air voids relative to control milling of the rumble strips. Kind of interesting, right? So you don't see necessarily a spike every time that you milled these rumble strips in. An example shown for Rock County, I chose a red line of 7% air voids, not as a pass-fail, not as a good or bad, just as sort of like a reference number, something reasonable that a lot of states use, something near for density requirements, just to show you, at least for this county, these are densities of the actual core joint that are pretty good, actually, right? 93% GMM for most of these on average. But we don't really see a spike in air voids with milling the rumble strips. But that's not to say that we can't pick up differences, especially when we apply these material treatments. And interestingly, although we don't see a measurable change in the air void content, we see a very measurable change in the extracted asphalt content. So for the VRAM sections, about a 2 to 3% increase offset from the control. It's not correlating to air voids, but it's there. It's measurable. It's kind of an interesting concept. A much lower increase, but still measurable for the asphalt emulsion fog. Now, that stands to reason. The fog is applied at a much lower rate than the VRAM is, so we would expect it to show up as lower change relative to control. But we can pick up the asphalt content, even though that's not shown in air voids. And we ask ourselves why that might be. Now, this is data taken from a different VRAM project, but it's representative of the VRAM sections that we've got in the 3 research projects for this NRRA study. This is a good visual representation of how the VRAM product works. More interesting than the actual air void content, like the magnitude of air voids, is the distribution that we see. So this is the distribution of air voids in the upper layer of a control sample, no VRAM whatsoever. We see this sort of parabolic distribution with the maximum density occurring kind of in the mid-depth of that layer and sort of very high edges. Makes sense, right? The edges are higher asphalt content. The VRAM actually takes advantage of this. It's applied between the layers. You can see this thick band of VRAM left over. As that new layer is paved on top of the VRAM, some of it, you could say, migrates or wicks up into that upper layer, filling the void distribution in the lower portions of the top layer, hence the name, void reducing asphalt membrane. And that's shown here. So this is data taken from a CT scan of the upper layer. That's how they can get all the various depths. And then that information's fed through a machine learning algorithm, actually. You can find that report here. But we see very low, approaching 0 air void contents at the kind of the interface where that VRAM is really concentrated, but then a similar distribution to control as we get into the upper portions of that layer. In other words, testing something like air void content as a bulk property, as of the upper layer itself, may not be as useful because there's a heterogeneous distribution of asphalt content in this case, of where that VRAM acts. So testing these cores in bulk performance, so like ideal CT or Texas overlay tester, even permeability, is probably a better idea to make inferences for performance than something just like a surrogate like air void content or even asphalt content, because it's not distributed in a homogeneous way. Well, how about permeability? You know, the good and bad thing, good for the counties that built these projects, maybe not so good for the research team. All of the projects we measured, even the control sections with no treatments at all, were would be considered impermeable. Call the impermeability whatever cutoff you want. In these units that I show here, some references 100, some reference units of 125 or 150. It doesn't matter. All of our values are very, very low relative to what would be typically considered a permeable mixture. Again, dense fine mixtures, compacted pretty well, water impermeable. Nevertheless, we can draw some trends. They're not going to be statistically significant, maybe not even practically significant, to be honest with you. But in general, we did see the centerline rumble strips did not, on average, cause an increase in permeability. Now, this is not in agreement with what had been reported in the literature prior. Granted, different mix designs, different construction practice, and so forth. For these mixtures, no increase. On average, these material treatments reduce permeability, but again, very low permeability sections. Little to be gained from that testing. Moving to performance, first, ideal CT. Many of you, I'm sure, are very familiar with this test. We don't need to labor on how this is run. I just put this up here because I wanted to show again how we ran the field cores, and that was with the orientation of the joint vertical along the load line. And the way indirect tensile testing works is these two sides of that joint would be pulling themselves apart. So we'd be actually inducing a tensile loading at that joint, pulling the joint apart. And you're measuring displacement, load versus displacement, right? So how that load is carried, and then how that core is sort of deforming under load. The CT index is an index that's a calculation that takes into account the entire testing curve, right? So it's just a single number. One good thing about the ideal CT test, I'll say, for doing what we did, is that you can correct for sample thickness. So our sample thicknesses were not the same, even core to core, because of differences in paving practice and so forth, certainly from just a structural point of view, design point of view. So we can correct for that. So CT index is nice because it's just 1 to 1 to 1. You can index versus the same regardless of the height, within reason. Those of you familiar with CT index, larger is better. A higher number is purportedly related to better crack resistance in the field, fatigue cracking resistance. This is an example from Sheboygan County, and let's just kind of zoom out and say, well, what do we see when we look at the data taken as aggregate? CT index typically suffers from, especially from field samples, relatively high variability. That's what the error bars show. But still, nevertheless, we do see some differences. But the first thing that comes to mind or comes to eye here is that the observed magnitudes of the CT index, for anyone familiar with that test, are very high. So these numbers are above what you would find for SMA mixtures, at least regionally, certainly above what we'd find for dense graded mixtures, maybe even hundreds of times above what we would see. Now, granted, these are plant-produced, so you could say short-term aged because they were cored right after paving, but still, these are very high numbers. We also noticed, as we do air void contents among the sections, a specific and then among the different projects, very different air void contents. The CT index, like most performance tests, is run at a target air void content, usually 7%. Our mixtures varied from 7%. So how do we account for that? That could be some of this variability as well. But the big one is probably that we're testing this giant discontinuity in our sample, right? Usually CT indexes are run on uniform lab pills or field cores that don't have such things as a joint in them. So the presence of the joint. So rather than use, well, let me back up. But even with all of those still in place, what do we see? Well, we see in this instance maybe a slight reduction as we move from control to rumble strip, some increases as we treat the control with these various treatment process. That holds true for the rumble strip. So there's something, but we decided a better way to use ideal CT would be to look through the load displacement curves themselves. In other words, the testing output. And unfortunately, what we found, really to sum this up for you, is that even when we control for air voids, um, when we control for air voids, we can normalize to height. We really found that the cracking behavior from the CT index point of view is just governed by the presence of that joint. It's the weak plane throughout the sample. It produces results that are likely violating some concept from the ideal CT test. So relatively limited information we felt we could gain from looking at this test more in depth. And that was similar for all three projects. So again, I know there's a lot more on this slide than I'm explaining, but I highlighted what's really important here is that really this test is not well suited for what we were trying to do with it. Wrong tool for the job. Nothing against the test necessarily. Let me mention one other important point not highlighted though. Our longitudinal joints, by and large, are not subjected to the traffic that the main line is. I mean, that they're construction joint. You're not really driving on it as much. In the ideal CT test, you're taking an uncracked sample, kind of assumed to be, intact sample. You're pressing on it until a crack forms that you could say that's kind of this like peak load area, and then how that sample progresses from there. But because these joints are not subjected to traffic, it's not really crack initiation that would dominate performance, right? It's some other property, and that's really what led us to choosing this overlay test procedure in the first place, is to simulate the construction joint. So in the Texas overlay tester, the way that this is set up for us is the sample is glued to these metal plates, and the joint is affixed right above where these two plates have a little gap. And it's a cyclic displacement controlled waveform. In other words, one plate moves relative to the other in a controlled way, cyclic, over and over and over and over again. It's an overlay tester. And there's really two metrics that we can get out of this. One is crack initiation. We've already kind of mentioned, maybe not the most important. The other is crack propagation. It's called the crack progression rate. How quickly will a crack grow through the sample? How quickly will damage manifest once the sample has a crack in it? Looking at the first parameter, crack initiation. So now this is all three projects shown: rock, wood, Sheboygan, control versus centerline rumble strip. And I'm choosing to show it this way as a statistical analysis. So same letter means that there is no significant difference between centerline rumble strip and control. And this would be taken over all of the centerline rumble strip sections, all the control sections, right? So it's treatment or not treatment. And what we found is really milling caused no change in the crack initiation. So another way to say that, no change in crack initiation along the joint. That's a good thing, right? They didn't directly damage the pavements in this instance. But much more interesting is this crack propagation. I mentioned this research study from Oregon about micro cracking being present after the milling of centerline rumble strips. And what crack propagation is doing in the overlay test is it's saying, all right, a crack is there. How quickly is this crack moving through the sample? And you can measure that based on the outputs of the test. So same setup here. The three county projects shown independently, control versus centerline rumble strips. And now we see clear directional trends, and we also see a statistical difference. In other words, in this instance, what we're finding is that the installation of milled centerline rumble strips statistically significantly increases the crack progression rate relative to control. In other words, taken at everything else average, the presence of the rumble strip allowed the crack to propagate through the sample at a higher rate relative to control. Important finding. We said, and maybe I should have had this picture in the earlier slide, but I really like it because it's showing you exactly what this tester is doing. So this is obviously a milled sample. So you'd be looking at like the center of the rumble strip glued to these metal plates, and I can see my crack right here. I'm going to follow it with my laser pointer. I put an arrow on it, and you're literally measuring the rate at which that crack progresses through the sample. And we said, right treatment at the right time for the right job. Well, to slow crack progression, one option would be greatly increase the asphalt content in the sample. And that's something that VRAM does. We've shown that with the asphalt content analysis, but also the CT scans. And what we found is that, yes, milling of the rumble strips significantly increased crack progression rate. These material treatments, at least the VRAM that we chose, can not only offset that effect, but it can kind of greatly enhance the durability of that joint relative to control, even beyond what the rumble strip was able to take away from it. So we found VRAM to be much more effective, likely because of the concentration of polymerized asphalt at that interface and concentrated in the lower layers where the crack is trying to propagate through. So in this instance, this chart, lower would be better. This is one of the 3 counties, trends consistent among the 3 counties. Kind of a hard shift of gears now. So we understand the performance aspects in terms of like material performance, but what about the functionality? And when I use the word functionality, I've also called it serviceability. What I'm talking about is driver alerting noise, so the ability of the rumble strip to tell the driver you've departed the lane, but also external noise, which for any of the design engineers here that work in urban environments, they know that installation of centerline rumble strips, it can be a little bit of a controversial issue because of nuisance noise or noise pollution. And I didn't know this more as a materials individual, but up until this last few years, it wasn't a widespread standardized way to measure functionality of rumble strips. And in fact, that's what NCHRP 1568 set out to do, was not only figure out what geometry of rumble strip would create effective low noise, and they mean external noise, but still safe rumble strips, but also come up with a method to do that, a standardized method. And it just so happened that this was wrapping up as we were starting this study. So we were able to hire the folks that did that study, that were the principal investigators of the NCHRP study, as consultants for the current NRRA study. And the way we set this up, it's on the project webpage. It's just a standalone consultant report. It's so removed from the materials testing portion of it, we decided just to upload it as its own report as delivered from the consultant. The consultant was Illingworth and Rodkin, by the way, if anybody is in that testing arena. This is data taken from the NCHRP 1107 report, and I debated whether to show this or not, but I do think it's useful. This is showing interior noise interval or increment, and what this means is the noise when you are not driving on the rumble strip versus when you are driving on the rumble strip. It's that change in decibels. Decibels is an interesting unit. It's not linear. Like a change of 1 decibel to 2 decibel change, 2 is not double 1. It's a logarithmic type of scale. So small change in decibels is a very large change in perceived noise to the human observer. But in general, what you're looking for is higher on-off interval. So bigger is better to alert the driver. Makes sense, right? You want to startle the driver into, okay, you've departed your lane. But a lower on-off interval from an external noise point of view is desirable for nuisance noise. In other words, when a driver accidentally crosses the rumble strip, you don't want the surrounding public to be alerted to it. But background matters, and I'll explain why that is in just a moment. And what these folks found from the NCHRP report is that treatments that impact background noise, geometry, or both have an impact on the safety interval, the internal interval. Now, what they found is that 2 of the sections they tested had been chip sealed immediately prior to them going out there and testing functionality. And because the chip seal changed the cross-sectional geometry of the rumble strip, and it changed the background noise when they were off the rumble strip, it negatively impacted that driver alerting interval. Now, be very careful, and the reason I said I hesitated to show this slide is this is not an indictment on chip seals. It's just the findings that they have. What I would advise is chip seals are absolutely a cost-effective preservation type treatment and should be used. Just consider the geometry of the chip seal in terms of aggregate sizing relative to the rumble strip geometry, or how you might lay out that project before doing it. The results, not our results, just the results here. We didn't include chip seals in our project for a number of reasons, but it's worth the note on geometry. Taken from the consultant report, internal on-off interval on the left, safety, external on-off interval on the right, nuisance noise pollution. So on the left, higher is better. This green line of 10 decibels, by the way, is sort of the industry accepted interval for performance. Anything below 10, marginally effective at alerting the driver. Anything above 10 considered to be effective for alerting the driver. And what we found, our baseline case, so this seafoam green kind of color here is the average of all three projects. So maybe let's just look at that one. Had such a high interval to begin with, it was very likely that our treatments were not going to negatively impact below this 10 decibel. And by and large, well, not by and large, that is what we found, is that the treatments did not impact driver safety. They did not change geometry. They were built on brand new, good condition pavements with low baseline noise to begin with. They maintained that driver safety. So paid a lot of money basically to figure out what you kind of already knew. But maybe more interesting was the nuisance noise. So now the green line is not some reference to an accepted value. It's a reference to the control. So relative to baseline, do the treatments change perceived external noise? And interestingly enough, they did across all scenarios, all projects, save for one. All right, and I think the consultant made some notes on that particular one, but nevertheless, let's just take the average. Reduced. And it's kind of interesting. How would that be possible? Well, we didn't do a lot of deep diving, but the hypothesis is because you changed the asphalt content and the air void distribution at the joint because of these treatments, you didn't change the geometry, but you changed those two things. It's likely that had an impact on external noise. It's what the data showed. Now, why it remains an open-ended conversation. But interestingly, and call it like, to steal a Bob Ross quote, a happy accident, right? That's what we found, is that nuisance noise was reduced. Early in this study, in the development of the work plan, we attempted to include long-term aging of half of the field cores. So this would have been taking the cores, but putting them in a forced draft oven. We ran into various difficulties, geometry differences of the cores, deformation of the cores while they were undergoing aging. We abandoned that. We elected to say, let's put all of our eggs in testing the cores as delivered, get more information from it. Because one of the major outcomes of this study is obviously that these research roads are built. They can be referenced in the future. Now, they're only 2 seasons old, so we're not really picking up any distresses at this point. But nevertheless, we ended with sort of predictive outcomes. What do we expect we should see? And we can validate that. In other areas of the upper Midwest that we do have treatment sections with the same material treatments, different mix designs, different traffic, even climate, you could say, control versus treated. We can use that for some sort of like directional validation. It's not validation because it's not the same project in a true sense, but directionally, are we correct or not? And what we've seen after 9 years, 8 years of service in these two case studies is in the VRAM sections, generally narrower crack widths, all right, and then lower incidence of what I would call incidence cracking, lower incidence of what I call ancillary cracking. So that would be cracking that's not at the joint itself, but it's associated with the joint, lower incidence of that. And what we found in our research was lower crack propagation rate. So the cracks are progressing at a lower rate, and that's by and large what our observations are showing us. So not to say we're validated, but to say, yeah, it appears that directionally we are finding what the field is showing us elsewhere. I mentioned in the onset, a deliverable for the project. It was a one-page sort of infographic. I just snipped that and put it here. This QR code will take you right to it. So you can download it. It's just a PDF, print it, do with it as you please. But being faithful to our objectives, does milling degrade mix at the joint? Do we have a damage multiplier? Well, the answer is, I guess, I underline here the most important point is the installation of milled centerline rumble strips is not the primary driver of performance. Underlying quality is. But the centerline rumble strip can influence things like the crack propagation rate. In other words, there is evidence that they can create the conditions that might accelerate degradation of the joint. We did find that we can offset and in fact move the other direction, those same properties using the material treatments. In the research we conducted, void reducing asphalt membrane was much more effective than the penetrating emulsion. That's not to say the emulsion didn't have an effect. It certainly provides a surface seal. It might help prevent longer term raveling, things that we didn't measure. Field observations will bear that out. But for this study, void reducing asphalt membrane was most effective. Neither of the treatments changed the safety features of the centerline rumble strip, so all of the good driver alerting benefits are maintained. So I'm going to leave you with kind of the main key practical outcome, and I apologize, it's at the bottom of your screen, but that's how the snippet worked. The advice is focus on building a good joint first, and use these material treatments. I called the centerline rumble strips potentially damage multipliers. Use these as durability multipliers, right? So as a way to increase reliability at your joint without compromising safety benefits. So that's the primary outcome of the research work. This QR code is just my contact information. It's just a little easier way than having to write it down if you'd like to connect. Otherwise, I do thank you for your hour with us, and again acknowledge the co-researchers I worked with, the research group folks, and Banking Materials, and then certainly NRRA. That's what I've got, Lauren. I know I'm running up on it, so if there are questions, hopefully we can get a few.
Yeah, I don't have any in the chat, but certainly if people want to unmute or Bernard's right on in there with his hand up. Bernard.
Yes, thank you for such a great presentation. You had Illingworth and Rodkin do, or rather you took their report or something. You didn't have them actually do the measurements, did you?
We did, yep. We had them come out and measure internal and external noise on all three of the projects in the fall of 2023, and their report to us is what's published on the NRRA page. Okay.
So did they use the statistical pass-by, or did they use the OBSI, onboard sound intensity, in their evaluation?
We did a modified version of their approach where we used one of the test vehicles, whereas in their NCHRP study, they recommend running several different vehicles. They did use both methods that you referenced. I just wanted to make sure I point out that they did follow a slightly different version of the testing than what was recommended by them in the NCHRP. Mostly a cost-driven decision there.
Okay, and finally, this great effort, did you, I know you have a report in the website, in the NRRA website, do you have a mndot publication? mndot publishes for NRRA. Is it a published report?
Yes, yes.
Okay.
The report, I don't know if the QR code it is published in their MnDOT library. That's correct.
Okay, good.
Yep.
Good. We can access it then. All right. Thank you very
You can
much.
access it. Absolutely.
Yeah. Thank you.
Yeah, the final report is linked on the project page.
Okay.
If you scroll down, you can see the last deliverable is the final report, and then also this one-pager infographic that they put together.
It's
Great.
this QR code. Well, we've got a couple minutes if anybody wants to scan it. Sorry, I'm going quick. It's this QR code. We'll take you to all that info.
Yeah.
All right. Thank you.
We did get another question in the chat from Jaron. Did you use any numerical method or software to quantify the crack propagation?
It's a software for the Texas overlay tester. So analysis for that test. I guess it would be, yeah, numerical method for that, the data output.
All right, she says thanks. I'm wondering if someone else is unmuted to ask a question here. Jay?
Yeah, hey, Dan. Yeah, I do have one question. First of all, great presentation, very easy to follow, very thorough. I appreciate it much. My question is, do you think, rather than like you said, the ideal CT really didn't show a lot. You think, due to the tension aspect of a DCT, you think that would have shown any difference?
I think so. I think that would be a more reasonable testing setup because you can isolate the loading right at the joint. The ideal CT, it's a little bit of a, you gotta, you're assuming the joint's running halfway and halfway. That's not always correct. These are field cores. Something where you're pulling at it, whether it be a thermal induced stress like the DCT, even something like an SCB where you're forcing the crack through the joint could be a little better. There's a careful balance, Jay, as you know, between making Swiss cheese out of a full-scale road and testing everything you can, and gambling, right? Ideal's easy, just unfortunately cheap and easy and right sometimes don't all align.
Perfect. Thanks.
I did get another question from Christine. Any plans to repeat the testing after the bituminous ages a few years?
Oh, for sure. Yeah, that's the probably the greatest achievement of this project, of the research project, is that 3 full-scale roads were built. So we can go out there and core. It's a matter of which interval makes sense. Long term, we don't all have the time to wait, right? We want to know, is this something I can implement right now? So maybe a 5-year check and coring would make sense. But absolutely, that's the plan, is to keep on these things over time. Both and both functionality and performance, by the way. We can redo the noise testing too.
I got another question here from Di. How is the critical fracture energy calculated for the overlay tester?
Ooh, that's a good question. I'm not the overlay tester expert, and I don't know if my co-authors and researchers are on here, if they can chime in, that would be great. It is definitely outlined in the final report. I don't want to misspeak though, so I apologize. I can't give you a direct answer. Certainly outlined in the report.
Okay. He says thanks. I do see a number of other thank yous for the presentation. And a note that Illinois DOT is looking at a centerline rumble program, so they're thankful for this timely presentation.
Oh, great.
We are over time now, so I will let people go if they need to run. And you've provided your contact information, so hopefully people grabbed that. But if anybody needs it still, they can certainly email me and I can pass it on to them.
Sure.
So thanks, Dan.
Yeah, and I can hang on, Lauren, for a couple minutes if there's someone that's just dying to ask a question. I'm certainly happy to help. So
sure.
But everyone, I appreciate it. I know we're running past, so thank you so much for showing up and asking good questions.
Yeah, well, if there's any other questions, then feel free to just unmute if you want to ask that. I'll give it a few moments here.
Yeah.
I do see the our attendance number is running down. People needing to jump off.
Dan, peak count, Wisconsin DOT. Great presentation. Interesting that, you know, it didn't really affect permeability statistically, you know, significantly. And with Illinois gearing up to do this, it'd be interesting for a coarser mix to see what impact this would have.
Yeah.
I'm sure it would affect the permeability then.
Yep. I agree, Pete. We make our mixtures very fine, very dense in Wisconsin. And in my experience, both in field permeability and lab measured permeability, is that the historically referenced numbers of 6, 8, 9% representing that sort of inflection point where permeability just skyrockets is actually doesn't really hold as well for our mixtures up here. Our mixtures tend to be pretty impermeable, even at those air void contents. And I'm referencing both NCAT permeability and lab. So you're absolutely right. And I was careful to say, like, does that still apply for SMA? Does that still apply for coarse grade? I don't know. Some of it is density driven, there's no doubt, but some of it's also just that aggregate packing, you know, how the void structure comes together. So these are all, Pete, for your reference, these would be our WISDOT LT, low traffic. So these would be 40 gyration mixtures, all three of them, 40 gyration design mixes.
Thank you. Yeah, just had that comment. It was very interesting to see that. So
yeah.
All right, great. Again, great presentation, Dan.
Thanks.
All right. Take care.